Hello everyone, welcome back. So I have completed the colloidal dispersion previously according to your syllabus. So from today onwards, I will start the next unit, or you can see in your syllabus, that is the rheology. Right. So first of all, we have to know what is rheology actually. So you can see the definition that rheology means this is the science or physics that concerned with the flow of liquids and the deformation of solids. So both. So here we actually discuss the flow of liquids as well as the deformation of the solids. So both things we have to keep in the mind. Okay. Next point, the study of the flow properties of liquid is important in pharmacist working in the manufacture or several dosage form, that is the simple liquids, gels, ointments, creams and pastes. So I think you have just already understood that in different dosage form is there, solid dosage form, liquid dosage form, but if I consider only the liquid dosage form, so different types of dosage forms is available in under the liquid, like a gel, ointments, creams, pastes. Okay. So those are actually coming under the liquid, and on pharmacists to know their the flow property. Okay, because from this kind of flow property, so other pharmaceutical parameter like their solubility, like the dissolution, all those things will be actually can be monitored. Okay, so this is actually important, the rheology. And this system change their flow behavior when exposed to different stress condition. Means, so if you give some stress, so the viscosity or the flow property can be changed. When you have just taking off those stress, or you can call that you have when you have just taken off those kind of stress which is provided earlier, so there might be some difference in the flow behavior can be happen. So now the questions may be arise that what is stress. So I will discuss it later. Okay, in the next slide. So the same things is discussed here. The rheology from the Greek rheo means to flow and logos means science. So it was suggested by Bingham and Crawford. Okay. To describe the flow of liquids and deformation of the solids. So viscosity is an expression of the resistance of the flow fluid of flow. So when you are talking about this kind of rheology, so one parameter is very much essential, that is the viscosity of the fluid. So viscosity, what is viscosity? Now viscosity is simply, if I can tell, that is the resistance, something which is give to the prevention during the flow of any kind of fluid. Okay, this is the obstacle you can call it. Okay, so that is the viscosity. Now it is saying that in the higher viscosity, if the viscosity is higher, so the greater the resistance. So this is very common things, that if the viscosity is higher means the resistance is more. Okay, so now from the pharmaceutical aspects, what are some the significance or application of the rheology which is discussed here. First of all, the formulations of medicinal and the cosmetic creams like paste and lotion, all these things is important. And formulations of emulsion, suspension, suppositories, tablet coating. Suppository is also kind of dosage forms which is actually gives in this kind of in the anal canal or anal route you can call it. And fluidity of solutions for injections, and in mixing of the flow of materials, when you have just perform or undergoes any kind of mixing process, so they are packaging into containers, the removal prior to use, the pouring from the bottle, so all those things actually depends upon the rheology. Okay, and the extrusion of a paste from the tube means when you try to take some paste from any kind of tube, like in daily uses you can consider like Colgate toothpaste. Colgate is a brand name, but if I consider one toothpaste, so from that if you try to remove some kind of paste, so that is called the extrusion of paste. So this is also example, like if you give some force means the stress, so the viscosity will be in decrease and it will be easily comes out from this kind of tube. So that is one type of example you can consider. Okay, and the passage of the liquid to a syringe needle, influence of the choice processing the equipments in the pharmaceutical manufacturing. So all those things, the choice of process, by using which type of processing, the mixings would be like which way, so that is depend upon the rheology. Okay. Okay, the next slide comes that pharmaceutical also just continually discuss all those thing aspects, like can affect the patient's acceptability of the product, physical stability, biological availability, all those things. So I can give you one example, like if you say that proper toothpaste, if it is not proper, you can say patient, not the patient but the consumer acceptability is not the up to the mark. I mean, if you are giving some kind of force, but the toothpaste is not coming out of the tube, so it is not the I mean the consumer acceptability. Okay, consumer will not be happy to accept all those things. Okay, that will not, I mean, fulfill the consumer acceptability. So this kind of things. So also, if you call the ointment, also ointment and different types of paste which is actually used in the pharmaceutical point of view, the same things, I mean, if it is not comes out from the tube after giving some kind of force, or you can precisely call stress from rheology point of view, so obviously the patient will not, I mean, comfort to use all this product. So the patient's acceptability will be not up to that much point. Okay, that is actually called here. Okay, so also the manufacturing of the dosage forms, mixing, flowing through the pipes, because if the viscosity is more than the normal, so that there should be some kind of problem while the flow will be happen, isn't it? And filling into the containers, that will be also little bit very tough if the viscosity is more. If you try to pour or fill some kind of solution or liquid into a container, its viscosity should be not that much or not that much low also. It should be optimum. But if the viscosity is become higher, so what will be happen? So it will be really hard to fill the liquid in the particular containers. It may be any kind of pharmaceutical syrup, okay, lotion, all those things. And handling of the drugs and administration, the syringeability, I mean, with the help of, with the aid of any syringe, if you try to pull up any kind of medicine, or pouring means it's a filling of liquids in the container, extrusion of ointment I have discussed in the earlier also. So all things actually depends upon the flow behavior of the dosage form. I mean, first of all, the viscosity will be increased. After giving some kind of force or stress, the viscosity will be get decreased and it will easily comes out from the tube. So that is actually discussed here. Okay, so this all the pharmaceutical aspect for the rheology. So now comes down the Newton's law of flow. So here actually you might get some kind of knowledge regarding the stress, viscosity, all those things. So actually try to visualize the block. Here what actually stated, like if you consider this block, so the block actually taken into the assumption like a liquid consisting the parallel plates. You can see here the plate. Okay, so just let me use the I mean, let me use the pen. Okay, just wait for some moment. Yes, so you can see that the plates are in a parallel way. Okay, so the molecules of this is actually like a liquid similar to a deck of cards shown in the picture, figure number 19.1. So if the bottom layer is fixed, means this layer is fixed, this layer is fixed, and the top plane is moved, top layer is moved constant velocity, each lower layer will move with a velocity directly proportional to the distance. Okay, means what happened, now the lower surface it will obviously have some velocity, the top surface it also have some velocity, but the velocity is not same. You can see the top portion it actually little bit left behind from the, sorry, the bottom portion, this is little bit, I mean, left behind from the top portion. What is the reason behind it? Due to the viscosity, resistance. Okay, you can call. So like here actually it is called that the each lower layer will move with a velocity directly proportional to distance means that portion, distance between the top layer and the bottom layer. So from the stationary bottom layer, the difference of the velocity dv, little change in the velocity taken as dv between the two planes, liquid separately by a infinite seminal distance dr. So dr is the little change in the distance and dv is the little change in the velocity. Okay, so dr, the velocity gradient or rate of shear, dv by dr, the force per unit area F by A required to bring about the flow is called the shearing stress. So try to understand. So F naught by A, that is actually the, you can call the shearing stress, and given to the symbol F. Okay, now Newton was the first to study this kind of flow properties of liquid, and Newton was the first to see this kind of study all those properties, and he recognized the higher the viscosity of any kind of liquid, the greater the force per unit area. Means the higher the viscosity, the higher will be the shearing stress. Newton has stated this required to produce a certain rate of shear. So rate of shear is given as symbol G, capital G. Hence the rate of shear should be directly proportional to shearing stress. Okay. So that is the point. So eta is the coefficient. Eta means this term eta. Eta is the coefficient of viscosity, usually refers to simply viscosity. So here you can find out that what does the term F naught A, that is the force per unit area. Force means F naught and divided by A means the area. So the velocity gradient or rate of shear dV by dr, that is proportional to this kind of, you can call that force per unit area. So the rate of shear and the shearing stress, it can be proportional. Okay, and eta is the proportionality constant, which is also called as the coefficient of viscosity. So this is all about the Newton's law of flow. Okay, so after that, frequently the equation eta equal to f by f divided by g, where f equal to f naught by a, because we have already called that f is the, what is this shearing stress, and f naught by a, that is also the same things, I mean the force per unit area, and g means the rate of shear, means the dv by dr, a representative flow curve or rheogram obtained by the plotting f versus g. You can see all in the curve also. Okay, this curve, I mean you can consider this curve, sorry, yes, this curve. Here you can see in the y-axis the rate of shear is taken, and the shearing stress in the x-axis, in the x-axis and the y-axis. Okay, so here you can see that F versus G for Newtonian system shown, and implied by the equation 19/2 means this equation eta equal to coefficient of viscosity F by G. That is the equation. So eta means the slope. Here the eta means the slope, the coefficient of viscosity according to the curve. Okay, you maybe know about this term that y by x, y divided by x, that is also called as a slope also, if any graph is, I mean you have plotted. Okay, so now that an implied equation straight line passes through the origin is obtained, the unit of viscosity in the poise defined as the reference to 9.1 as the shearing force required to produce velocity. And what is the, I mean unit of his velocity is poise by defined definition of viscosity is the shearing force required to produce a velocity 1 cm per second between two parallel plates. The liquid is 1 semi square area separated by a distance of 1 cm. But if you take everything at unitary, like 1 semi per second, so then the viscosity can be defined like that way also. Why? Because you can see also, like if they previously, you can see also previously that the equation is actually like that. I mean f naught by a, I mean the unit area, that is taken as 1 semi square, like that way. Okay, okay. So rheogram, what is rheogram? Rheogram is a plot of rate of shear versus the shearing stress. For Newtonian liquid, if G is plotted versus F, the flow curve is straight line. Because Newtonian liquid, I mean all those things, it is constant. I mean with increasing the shearing stress, the rate of shear will be not changed. But I mean it is changed in a unitary, I mean the constant way. That is the things. The line passes through the origin and the slope is coefficient of viscosity. Okay. So what is shear? Shear is the movement of the material relative to parallel layers. Shear is the movement of the material relative to the parallel layer. And what is the shear stress? This is the force per unit area required to bring about flow. Means to bring about any kind of fluid to flow, what is the force actually required per unit time? That is known as the shear stress. And what is shear rate? This is the difference in the velocity dv. I mean if there is a difference like the top layer and the bottom layer, if there is any kind of velocity difference, that is known as the rate of shear. Okay, I mean obviously that should be separated by some distance, that is dr, taken as consideration. And I have already discussed the shearing stress actually proportional to the shear is dv by dr. Okay, that is also discussed here also. And shear stress is defined as the force per unit area which is applied to bring about the flow, we have already discussed. And velocity gradient or rate of shear dv by dr is defined as the change in the velocity dv with the infinite small change in the distance. So velocity gradient means, or the rate of shear, this is the same term, dv by dr. When we have giving some kind of, I mean force, so if there is any kind of flow is happened, so velocity difference should be there, top layer and bottom layer. And if the layer difference, I mean the distance between the two layer dr, so you can call the velocity gradient like a rate of shear which is dv by dr, means the change in the velocity dv with the infinite small change dr. Rate of shear also the same things. Okay, g equal to dv by dr. Higher the viscosity, that is the important, I mean the line, that is important line. The higher the viscosity of the liquid, the greater the force per unit area required to produce a certain rate of CR. Okay, that is the proportional. They are proportional. I mean the correlation. So that's why it like written like that way. The higher of the viscosity of the liquid, the greater is the force per unit area required to produce a certain rate of CR. Okay. So now the different types of definition is there, like the absolute viscosity. What do you understand by the absolute or dynamic viscosity? Dynamic means something is in, you can call like a some have some dynamic when variant different type point of view. Okay. So different, the fundamental unit of viscosity measured in the poise, material requiring a shearing stress 1 dyne per square centimeter to produce a shear rate of 1 reciprocal second has a viscosity of 1 poise or 100 centipoise. Or what is absolute viscosity? The equation is if not by S means the shearing stress by shear rate, or you can see the unit, that is a dyne meter to the power minus 2 second. Okay, that is the absolute viscosity. And what is fluidity? This is the reciprocal of the viscosity, because the viscosity means there is some resistance or obstacle of fluidity. So that's why it is written like that way. Fluidity means the reciprocal, means the opposite of the, you can show the called the viscosity. So that's why it is written like that way. And what is kinematic viscosity? Kinematic means something having motion or movement. Okay. So it is the absolute viscosity divided by the density of the liquid at a specific temperature. So when you have just divided the dynamic viscosity or absolute viscosity by the density of that particular liquid, so you can get the kinematic viscosity. Okay, so that is all about the definition. And relative viscosity also I have discussed here also. This is the relation of the solution viscosity to the viscosity of the solvent standard. This is the relative viscosity, and some example is there, you can see. Okay, this is the solution of the example, you can do it by yourself. Yeah, two questions is the viscosity of acetone is 25. Obviously in a particular temperature, you also remember the point, viscosity should be mentioned in a particular temperature also, the 25 degrees Celsius, 24, like that way, 37 degrees Celsius. Okay, so you can do the numericals by your own. So I will just go to the next slide. That viscosity and temperature I have already told you that should be, temperature should be mentioned why you have talking about the viscosity of any particular liquid. So so here you can see the where is the viscosity of a gas increases with temperature, but for the liquid it will actually opposite. I mean liquid, it decreases the temperature is, I mean when the temperature is decrease or increase, the viscosity can be decreased. So the opposite actually here, viscosity for the gas, I mean the viscosity of the gas increase with temperature, that of liquid decreases as temperature is raised. I mean the opposite case is for liquid. And the fluidity of the liquid, as it is reciprocal of the viscosity, increases with the temperature. So that it is a very easy concept, you can understand. The dependence of the viscosity of any kind of liquid on temperature is expressed approximately for many substances and analogous to the Arrhenius equation. You have seen the Arrhenius equation also. Eta equal to A to the power E EVRT. A is the constant depending on the molecular weight, and EV is the volume, molar volume of the liquid, and EV is the activation energy. Okay, that is the thing. So what is the relation between the viscosity and temperature for gas and liquid? So you have to well aware of these things. Okay. Okay. Now we have already discussed about the Newtonian fluid. Like for Newtonian fluid, the curve will be in a straight line manner. Okay. But the non-Newtonian fluid is defined as one for who is the relation between the F and S is not constant. Means the shearing stress and rate of shear. Talking about that only. The rest shearing stress and rate of shear, that is not constant, which is constant for the Newtonian. As that reason the graph is straight line, but for non-Newtonian the relationship is not like a constant. So in other word, when the shear rate is varied, the shearing stress doesn't vary in the same proportion. The viscosity of such fluid will therefore change as a shear rate is varied. Okay, it can be seen in liquid and solid heterogeneous dispersion, some as colloids, emulsion, all those things. So main things is that there is no, you can find the, I mean the relationship is not like a constant between the shearing stress and the shearing rate. And the mainly three classes are here, although time independent, time dependent, all those concept is there. So time dependent you can call all those thixotropic and rheopexy, I will discuss this later, but time independent, these are the plastic, pseudoplastic, dilatant. So first of all I will discuss the plastic. Okay, I will discuss the plastic. So plastic flow is associated with the preparation of flocculation or aggregation. So particularly this terminology you have to keep in mind, that flocculation is associated with the plastic. Floccule means some kind of aggregation is will be formed. This kind of aggregation will be formed. Just let me draw. Floccule means this kind of aggregation will be done. This kind of floccule aggregation will be, I mean there should be like that way. Okay, so particles in concentrated suspension known as the Bpharm bodies. So Bpharm bodies doesn't begin with to flow until the shearing stress corresponding to the yield value. Means you can see in the, just let me zoom the picture, that here the shearing rate of shear is changed, but after a certain period of time. I mean it's not like that from origin the shearing stress changed, all those things have been started, it's not like that. After, I mean you can call like obtaining the particular amount of shearing stress, the rate of shear or change in the shear will be happened. Okay, so that is called the yield value. Like the plastic deformation, when you have just initially, when you give any kind of force, the plastic will be not deform, I mean it will not break, but after a certain period of time when you apply the more force, it will suddenly break down. So that is the concept here. So here the plastic is considered like a solid materials, but there some flow property should be there. So after the yield point will cross, so if you apply some force after that point, so it will, I mean you can call the breakdown, or there's some kind of deformation. So the Bingham body doesn't begin to flow until a shearing stress corresponding to the yield value. And what is yield value? It is the indication of the force. I am talking about the force that must be applied a system to convert it into a Newtonian system. Newtonian system means it will flow. It will flow actually. Okay. Like what is the example? You have to really, I mean properly aware of these kind of examples. The suspension of zinc oxide in a mineral oil, certain paints and ointments, all these things are example of plastic flow. Okay. Okay, now we can see the example also. Certain shear stress has to be applied in order to have some kind of flow. The applied force has to be higher than the structural force. You can see. Okay, so first of all, the, I mean this kind of ointment is not come down, but after certain period of time when the force is 1 kg or the weight is 1 kg, suddenly it comes out from the tube. Okay, that is the thing. Paste, I mean tomato paste, chili paste, all those things actually demonstrate here. Okay, so now the slope of the rheogram is termed as the mobility and analogous to the fluidity, because the fluidity is reciprocal to viscosity in the Newtonian system, and reciprocal is also known as the plastic viscosity. Okay, so you have to remember that the slope of the rheogram means the curve, rheogram is the curve or graph, shearing stress, rate of shear, all those things, between all those things. Okay, so here the slope is actually mobility, which is analogous to the fluidity also. Okay, and in Newtonian system, and reciprocal is known as the plastic viscosity, that is u equal to capital F minus small f divided by s, or small f is the yield value. This is for the plastic. Okay, so this is all about the rheology for today's class, and calculating the plastic viscosity by using the formula, one kind of numerical fact. I mean calculated here. You can see this numerical. So from next day onwards, I will start the pseudoplastic and so on. Okay. So thank you for today, and if you have any kind of doubt, you can ask me in the comment sections. Okay. Thank you.